Application: finding side lengths using specific ratios. In our previous lessons, we spent quite a bit of time deriving the specific trigonometric ratios for certain key angles, specifically 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. We worked hard to understand where those values come from. But you might be wondering, why did we learn all those specific values? Well, that brings us to the primary purpose of this lesson. These values are powerful tools that allow us to calculate unknown side lengths in a right-angled triangle. As long as you are provided with just one side length and one acute angle, these ratios give us the exact information we need to solve the rest of the triangle. Welcome, everyone. Let's begin our new lesson on the application of trigonometric ratios. Now, if you look at the first slide, you'll see our topic: application: finding side lengths using specific ratios. In the next few slides, I am going to walk you through a systematic strategy to ensure you are always selecting the correct ratio to find those missing sides. The strategy for solving. Now that we've recalled those important trigonometric values from our previous lesson, let's talk about how we actually use them. To find an unknown side, you shouldn't just guess which formula to use. Instead, you must follow a systematic approach to ensure you are applying the correct trigonometric ratio every single time. Our first step in this process is to identify the given information. First, take a close look at your triangle and note the measure of the given acute angle. For example, theta equals 30 degrees. Once you have the angle, look at the side length you already know. You need to determine its role relative to that specific angle. Ask yourself, is this side the opposite side, the adjacent side, or is it the hypotenuse? Identifying this correctly is the foundation for the next steps we are about to discuss. The strategy for solving continued. Now that we have completed step 1 by identifying our given angle and the side we already know, we move on to step 2. This is where you clearly define your goal. Look at the triangle and determine exactly which side is missing. You need to decide if the side you are looking for is the opposite side, the adjacent side, or the hypotenuse. Once you know what you are looking for, we move to step 3, which is perhaps the most critical part of the process: selecting the appropriate trigonometric ratio. To do this successfully, you must choose the ratio that acts as a bridge, connecting the given side you identified in the previous step to the unknown side you just identified. Let's break down your 3 options. First, if your problem involves the hypotenuse and the opposite side, or if you already have the opposite side and need the hypotenuse, you will use the sine of theta. Second, if you are working with the hypotenuse and the adjacent side, or vice versa, you should use the cosine of theta. And finally, if your calculation involves the relationship between the adjacent side and the opposite side, you will use the tangent of theta. Remember, the key is to always look for the ratio that links the information you have to the information you need. The strategy for solving continued. Now that we have identified our sides and selected the correct trigonometric ratio in the previous steps, we move to the final part of our strategy. Step 4, which is to substitute and solve. First, you will take the known values we identified in step 1, such as your given angle and side length, along with the specific numerical value for that ratio from your summary table, and plug them directly into your formula. Once everything is substituted, your goal is to solve the resulting algebraic equation. This usually involves performing some basic algebra to isolate the unknown side on one side of the equals sign, leaving you with your final answer. We will practice this exact process in the upcoming worked examples. Worked example 1, geometric application. Now that we have established our step-by-step strategy for selecting the correct trigonometric ratio, let's put that theory into practice with our first worked example. Take a look at this problem involving a geometric application. We are presented with a right-angled triangle labeled ABC. Where the right angle is located at vertex B, we are given 2 specific pieces of information. First, the measure of angle C is 30 degrees, and second, the length of the side BC is 6 centimeters. Our objective here is to use the values we know to find the lengths of the remaining two sides, which are side OB and the hypotenuse, side AC. As we move through the next two slides, I will show you how to apply our strategy to find each of these sides one by one. Worked example 1, geometric application, finding side AB. First, let's clearly list what we know. We are given that the angle C is 30 degrees, and the side BC, which is the side adjacent to our angle, has a length of 6 centimeters. Our goal, or what we need to find, is the length of the opposite side, which is side OB. Next, we need to choose our tool. Looking back at the strategy we discussed earlier, we need a ratio that connects the adjacent side to the opposite side. Since we have the adjacent side and need the opposite, the tangent ratio is our best choice. So, we will use tangent of 30 degrees. Now, let's perform the calculation. We start by setting up our equation. Tangent of 30 degrees equals OB divided by BC. From our special angles table, we know that the value for tangent of 30 degrees is 1 over the square root of 3. So, our equation becomes 1 over the square root of 3 equals OB divided by 6. To isolate OB, we multiply both sides by 6, which gives us OB equals 6 divided by the square root of 3. Now, in mathematics, we prefer not to leave a radical in the denominator. To fix this, we rationalize the denominator by multiplying both the top and the bottom by the square root of 3. This gives us 6 times the square root of 3, all over the square root of 3 times the square root of 3. Since the square root of 3 times itself is simply 3, our fraction simplifies to 6 root 3 over 3. Finally, dividing 6 by 3, we arrive at our final answer. OB equals 2 root 3 centimeters. Now that we have set up our problem in the previous slide, let's walk through the actual calculation for finding side OB. Keep this value in mind, as we will use it in the next slide to find the length of the hypotenuse, side AC. Worked example 1, geometric application, finding side AC $. Let's start by reviewing what we already know from the problem statement. We are given that the angle C is 30 degrees, and the length of the adjacent side, BC, is 6 centimeters. Our goal now is to find the length of the hypotenuse, AC. To decide which trigonometric ratio to use, we look at the relationship between our known side and our unknown side. Since we have the adjacent side and we are looking for the hypotenuse, the cosine ratio is the perfect tool for this job. So, we will use cosine of 30 degrees. Now, let's walk through the calculation step by step. We set up our equation by stating that cosine of 30 degrees is equal to the length of side BC divided by the length of side AC. From our special angles table, we know that the value for cosine of 30 degrees is the square root of 3 over 2. Substituting this into our equation, we get the square root of 3 over 2 equals 6 divided by AC. To solve for AC, we can cross-multiply. This gives us AC equals 6 times 2, all divided by the square root of 3, which simplifies to 12 over the square root of 3. To make our final answer cleaner, we shouldn't leave a radical in the denominator. So, we rationalize the denominator by multiplying both the top and the bottom by the square root of 3. This results in 12 root 3 over 3. When we divide 12 by 3, we arrive at our final result. The length of side AC is 4 root 3 centimeters. Now that we have successfully found the length of side OB in our first example, let's move on to finding the final remaining side, which is the hypotenuse, AC. In the next slide, we will see how we can apply this same systematic strategy to a real-world scenario involving a ladder. Worked example 2, real-world application. Now that we have mastered the geometric approach in our first example, let's transition from abstract triangles to a real-world application. Take a look at this problem on slide 8. Imagine a ladder leaning against a vertical wall. We are told that the ladder makes an angle of 60 degrees with the ground, and the total length of the ladder is 12 meters. Our goal here is to determine the height. Specifically, how far up the wall does the ladder reach? As we move to the next slide, we will break this scenario down into a right-angled triangle so we can apply the trigonometric strategy we just learned. Worked example 2, real-world application, solution. First, we need to perform step 1, which is to model the problem. Imagine the scene. The ladder, the vertical wall, and the flat ground meet to form a perfect right-angled triangle. To solve this, we must label our parts. The ladder itself is leaning diagonally, so it serves as our hypotenuse, and we are given its length as 12 meters. The angle formed between the ladder and the ground, which we'll call theta, is 60 degrees. Finally, the height of the wall that we are trying to find is the side directly across from our angle, making it the opposite side. Next, we move to step 2, where we select the appropriate ratio. Looking back at the strategy we learned in the previous slides, we ask ourselves, what do we have and what do we need? We have the hypotenuse and we need the opposite side. The only ratio that connects these two specific sides is the sine ratio. Now, let's proceed to step 3, the calculation. We set up our equation by stating that the sine of 60 degrees is equal to the height of the wall divided by the length of the ladder. From our specific ratio summary table, we know that the sine of 60 degrees is equal to the square root of 3 over 2. So, our equation becomes, the square root of 3 over 2 equals h over 12. To isolate h, we multiply 12 by the square root of 3 over 2. This simplifies beautifully to 6 times the square root of 3. So, our final answer is that the ladder reaches a height of 6 square root of 3 meters, which is approximately 10.39 meters up the wall. Now, let's move on to the solution for our second worked example, where we apply the strategy we just discussed to a real-world scenario. In the next slide, I will show you how we can use Pythagoras Theorem to double-check that this calculation is indeed correct. Verification using Pythagoras Theorem. Now, before we move on to some common pitfalls to watch out for, I want to show you a very important way to check your work. Once you have calculated all 3 sides of a right triangle, you don't have to just take your word for it. You can actually verify your results using the Pythagoras Theorem. As a reminder, the theorem states that the opposite side squared plus the adjacent side squared equals the hypotenuse squared. Let's apply this to the values we just found in our first worked example to see if they hold up. In that problem, we found the opposite side to be 2 root 3, the adjacent side was 6, and the hypotenuse was 4 root 3. If we plug these into the theorem, we get 2 root 3 squared plus 6 squared equals 4 root 3 squared. Let's break that down step by step. When we square 2 root 3, we get 4 times 3, which is 12. When we square 6, we get 36. And when we square 4 root 3, we get 16 times 3, which is 48. So, our equation becomes 12 plus 36, which equals 48. Since 48 equals 48, we have mathematical proof that our calculated lengths are correct. It is a great way to gain confidence in your answers before moving to the next step. Common mistakes to avoid. Now, before we wrap up our lesson, I want to pause and discuss some common pitfalls. Even if you understand the concept, it is very easy to make small errors that lead to incorrect answers. Let's look at 4 specific mistakes you should watch out for. First, there is the issue of incorrect side identification. It is very common to confuse the opposite and adjacent sides. Remember, these labels are not fixed. They change depending on which angle you are focusing on. To avoid this, always identify your sides relative to the specific acute angle you are using, rather than just looking at the right angle. Second, you might find yourself using the wrong trigonometric ratio, for example, using sine when you actually need tangent. To prevent this, I highly recommend that you always list your given side and your required side on your paper before you even attempt to pick a ratio. This keeps your strategy clear. Third, watch out for calculation errors involving radicals. Sometimes, students finish a problem but leave the answer in a messy form, such as 6 over the square root of 3. In mathematics, we prefer a clean, rationalized denominator, so make sure you convert that to 2 root 3. Finally, be careful with calculator or value errors. It is easy to accidentally grab the value for sine of 60 degrees when you actually needed cosine of 60 degrees. Whenever you are working with these specific angles, I suggest you always double-check your work against your summary table to ensure you are using the correct value. If you can avoid these 4 mistakes, you will find that your trigonometry calculations become much more reliable. Key takeaways. To wrap up our lesson today, let's review the key takeaways to ensure you have a solid foundation for solving these problems. First, remember the standard workflow we've practiced throughout these examples. Identify, select, and solve. Always start by identifying your knowns and unknowns, select the correct ratio based on those sides, and then solve the equation. If you follow this systematic approach, you'll avoid most common errors. Next, let's quickly recap the trigonometric links. Use sine theta when you are working with the opposite side and the hypotenuse. Use cosine theta when you are connecting the adjacent side and the hypotenuse. And finally, use tangent theta when you need to link the opposite and the adjacent sides. Lastly, don't forget that the Pythagoras Theorem is your best friend for checking your work. As we saw in our first worked example, once you have calculated your side lengths, you can plug them into the formula where opposite squared plus adjacent squared equals hypotenuse squared. If both sides of your equation balance out, you can be confident that your trigonometric calculations are accurate. Keep practicing these steps, and you'll master these applications in no time.